So let's start. Today is the 28th of October. We are at the class number 22nd already, and we cover, I think, pretty much like more than 40 hours of this class. Actually, more than what is really written on the course syllabus. Okay, so pick up from last time that we talk about the buckling load. We come up with the buckling load previously by solving the governing differential equation. So Eigen buckling. First, we get the load by solving the differential equation. The governing So we pose the boundary conditions, put everything in, and then we come up with the Eigen buckling load. We can also come up with the load by the second using stability functions. So if we use the stability function, actually we can cast the stiffness matrix of the column or of the frame. All right, we can do more than just a single column. If you cast the differential equation for the frame, that will be quite complicated. You have too many things going on. But this is a good tool. So we cast the stiffness matrix. And also the third option, which can be done also, we use the geometric stiffness matrix. Again, as the name suggests, it is a kind of stiffness matrix. This approach introduced the second order effect, and the derivation for the geometric stiffness matrix will be in the finite element course, because we are going to use the approximate deformed shape, which is a concept of finite element methods. So it will be in the next semester. Basically, I will derive these geometric stiffness matrix for you. For this course here, I just gonna give it to you and you can use it. All right, but the derivation, I try not to use the FEM, but still, if you don't have the FEM background, then the derivation of this could be like quite difficult to understand without the concept of FEM. So we're gonna adopt and make use of it, but don't worry, you're gonna see the derivation of this one soon. Okay, so the option number 2 and number 3 are very powerful. You will find out the buckling load of the frame or column by casting the equilibrium equation. But what kind of equilibrium that we're gonna get from 2 and 3? When you cast the equilibrium equation, you have the stiffness matrix multiplied by U, and then you get the force Basically for the buckling load effect, the force vector on this side is 0. You don't apply the force that cause basically the deformation of the structure. The structure we consider here could be the axially rigid structure. Okay, so what describes the buckling is that the state of the structure that you have the displacement, but you do not have the resistance. Okay, let's think about it this way. You have the displacement, mean, well, structure moves. You think of maybe just the column. You have this structure if the structure is axially rigid, or even though it is not axially rigid, if it still can deform along the axis. All right. You apply the load. Supposedly you should have the deformation just along the axis. But when the structure buckle, it's not just this deformation. You're going to have the deformation in the transverse direction. The transverse direction, we don't apply anything. Basically, we don't put anything, but it just goes transversely. You have deformation, and you do not have resistance. It just goes without applying any load. It just can go out of the straightness. Okay, so this is the buckling. So essentially, the right hand side force vector, you have nothing there. You have nothing, but your structure, your U, is non-zero. Okay, so how do we solve this? Right hand side is 0, and knowing that U is non-zero. Okay, so what will be inside the K? Well, if U is 0, then you don't need to do anything. That turns out to be the trivial solution. Am I right? So you have nothing. You don't apply any force, and you don't really have the deformation in your structure. So that means, well, 0 displacement multiplied by stiffness matrix turns out to be 0 external force, right? So that is one solution, but that is the solution that we don't really want to do. We don't really want to know. So we want to know the solution that what kind of K multiplied by non-zero U and makes the right hand side 0. How do we get this condition? The K has to be, the determinant of K has to be 0. Okay, so inside the K, if we look at the stability function, you have the how do we call F12 F6 minus F12 F6 F6 F4 minus F6 F2 minus F12 minus F6 F12 minus F6 F6 F2 minus F6 F4. So inside this stiffness matrix, all these functions They are varied with KL, which is the P over EI, or I could say that it depends on the P, the EI, and the length, these three parameters. When you do the buckling analysis, what is changing? L doesn't change. EI doesn't change. You have the fixed structure. The structure will not change EI all the time, increasing the cross section by itself. So the only parameter that change is the P. So as you vary the P value, all these stability functions changes, right? And then the value that makes the zero determinant will be the buckling load. So for the matrix, for example, if you have the 4x4, how many eigenvalues that you can come up with? In the reality, if you solve the problem using the differential equation, you have infinite roots. So you have the n pi, where n is the integer, 0, 1, 2, 3, uncountables. So you end up with that infinite roots. For the system like this, if we assemble everything into the stiffness matrix, and that depends on the number of degree of freedom. So you'll be able to find eigenvalues, which is going to be as many as the number of degree of freedom you have. It is like structural dynamic course. If you want to find the fundamental frequencies, well, you set up the m omega square and ku, right? And then you take out the u and you find out the omega square. That makes the determinant of m square, m and k, alright, v0, that expression. So you will find as many roots of omega square as long as you have n number of degree of freedom in your dynamic system. Thus, the finite element approach or direct stiffness approach generally makes the structure more stiff than the reality. Sometimes if the approximate deformed shape can pick up the real deformed shape, the structure will be as stiff or as soft as the real structure. But due to the nature of FEM, that this course is actually the subset of FEM, the direct stiffness approach. So due to the nature of FEM that the displacement is approximate, the solution is approximate. So it doesn't simulate the real condition, and that makes your structure a little bit more stiff than the actual structure. So the numerical solution will be more stiff. More stiff means you have higher frequency, you have higher stiffness, because your structure cannot deform in the way that it would like to deform in the actual situation. Alright, anyway, so we will be getting the many roots, many eigenvalues, and the smallest one will be your buckling load. It is the bifurcation problem. The bifurcation problem is like this. You have it could be the displacement, you could have the load P. So you think about the cantilever column raised on the fixed support like this. You apply the load, and if the U is the lateral displacement, axial load and lateral displacement, they don't relate, right? They don't relate. No matter how much you apply the axial load, if you solve your structure, using the equilibrium, you will not have the lateral displacement. So it goes like this. It goes just vertically. You have zero displacement as you apply the axial load. And once you approach the buckling load, here is your response. You get the infinitely large U value. This point is called bifurcation point. And if your structure survives this bifurcation point, which is not likely to survive, but that's just the if. If it does, then it's gonna go to the next bifurcation point. So that's another route. Another eigenvalue. Okay, because you don't have just one. But the thing is that your structure will buckle at the first buckling load. So you will not see the second bifurcation point, but it exists mathematically. Okay. Then let me give you the geometric stiffness matrix, which is also the relationship with the axial load, but simplify. You recall that the stability functions are made of the trigonometry function, basically a lot of sine, cosine put together. And that seems to be quite troublesome during the calculation. Sometimes your function is not well arranged, and then you have some sort of jumping of the value, function value. So it's not so friendly for the computer structural analysis, especially in the computer program for commercial use. They use the geometric stiffness matrix more. So the K comprises two parts. First of all, the linear stiffness. This one is just the 12.6 minus 12.6 EI over L cube, EI over L square. Something we derived before. Normal stiffness without the second order consideration, plus K G. So this part add on top of the linear stiffness. The geometric part adds in, and this part take care of the second order effect. So let's see how does the KG look like. it is minus P over L 6/5 L over 10 minus 6/5 L over 10. L over 10 to L square over 15 minus L over 10 minus L square over 30 minus 6/5 minus L over 10 6/5 minus L over 10 L over 10 minus L square over 30 minus L over 10 minus 2L square over 15 . So this part will be applied on top of the normal stiffness we had. And basically every single entry here is consistent with the entry in the linear stiffness. So for example, 12 EI over L cube term. EI, E is the unit of the force per square per area, right? Square of the length scale. So E multiplied by I, which is the length to the fourth. So you end up with force multiplied by length square, and you have 12 EI over L cube. Okay, so force times length square divided by L cube, you end up with force over length scale to the power of 1. And okay, here that 12 is consistent with the 6/5. 6/5 multiplied by P over L. P is a force, L is the length scale. So the same thing, okay, are put together. You cannot have any inconsistencies in the unit because you add these two up. Okay, right. So knowing all of this, we can move next into the calculation, maybe in the Microsoft Excel, in order to figure out the buckling load. Basically, let me just write down the problem that we will do in there, because we're gonna switch from this platform to the computer platform in a bit. So we can do this. We can also do something like this. Okay, so the first system here we could have the 3 degree of freedom, but the degree of freedom that take care of the axial deformation, actually it is not necessary, because it is not giving us any information about buckling load. You can just get rid of it. The second system here, the degree of freedom that we really have are the rotations at both ends. The third one, if we formulate this problem using just one element and we enforce the boundary condition, we lock the top, we lock the bottom, nothing happen, right? because you will eliminate all rows and column, you don't get anything. So we can just put the node there. Then we have 2 degree of freedom. The system like this, we have this, we have the translation in the x-axis, and we have the rotation there. In total, 3 degree of freedom. So if I may set up the local coordinates such that when we move there, we will not have to use the direction cosine. We just want to do some sort of quick calculation. You can use direction cosine, right? But I just want to show it. So I will let the local coordinate goes like this. So here is the first node, right, at the top, and then the transverse deformation just point towards the x, so we don't need any transformation. We just need to stuff the entries into the global stiffness matrix correctly. Just that. This is another C value, C coordinates. So I set it up in the same way. Same for this one, C point towards this. So both elements, top and bottom. So this is the last one. And there, this is the L over 2 and L over 2. This is the L. Let's make this one L as well. L and L. Before we go there, maybe we take a look at how we put everything out in from the matrix. So if you guess what's going to happen in the what you're gonna get, your buckling load will be the function of the EI and the L and some number, if you can guess from here, right? You have some parameters, but the P will be what you want to determine. You have the linear stiffness, which is just the function of the EI and the L. Okay? The geometric stiffness, you have the P, which is to determine, and the L. So once you solve, you will get the P as a function of EI and L. Okay. So I will write this. So the linear term, space is not enough. EI is out there, 12 over L cube. So we can take the L cube outside, and then 6L, right, minus 12 and 6L. The second line, 6L 4L square minus 6L and what else? 2L square minus 12 minus 6L plus 12 and minus 6L, 6L 2L square and minus 6L and 4L square. Arrange this a little bit. Actually, you will have the system that combine many structural members, but if we just consider one individual structural member for now, the right hand side will be what? All zero, right? We set up the equilibrium equation to determine the buckling load. External force, we set it to 0. So right hand side vector is 0 now. Everything here is multiplied by the deformation U. So you have U1, U2, U3, U4. First, I multiply through, this is actually the same, multiply through by L on the equation for the force equilibriums. So that are associated with row number 1 and row number 3. I just want to end up with just numbers inside the matrix and put everything out. So I did that successfully. The second thing, if I change the rotation into the degree of freedom that is equivalent to the length in a length scale instead of rotation, I pull out the L from inside the stiffness matrix and multiply by U2 and U4. So I have to take it out from the the column number 2 and column number 4. All right, I steal it out. So this gone, this gone, This look perfect now. I will just delete. I will cancel this out. So and likewise over here, instead of having LQ, then I have just L square, and I erase this. So P will be in terms of EI over L square multiplied by some number. What is the buckling load we used to determine? Pi square EI over KL square. Alright, so if you take out all the pi and k, which is the effective buckling length, factor out, then you will get the EI over L square, okay, which is consistent with what we did. For now, be careful the P, the sign convention for the P is compression. And that's why you have the minus sign in front of P. It takes care of P being the compression. So be careful with this part here, okay, that what kind of force the P is. If you want to put the P as a tension, then if P is tension and when P is negative is compression, then you got to take that minus sign out. Okay, don't just confuse ourselves. P is the compression. The thing is that this geometric stiffness matrix is capable for both tension and compression. You don't need to switch from one function to another like stability function. Because when you derive stability function, you have hyperbolic cosine when your system is subjected to tension, and just normal trigonometry function when you deal with compression. You need to switch, but this one is just good for both. Not as accurate as that one, but the accuracy is in the level that we are happy. So up to this point, when you find the determinant will be in terms of something multiplied by P, right, plus or minus something multiplied by EI over L square in this sort of terms. Okay, so let's play with this thing in the Microsoft Excel. Okay, so you have this from your homework. All these cells are made to calculate all four stability functions. So now we look at the first case where we have cantilever column. Cantilever column, if we set up the local coordinate pointing towards pointing downwards. All right, we will have the first two degree of freedom, transverse displacement and rotation, which are non-zero. So the first two are the 12 EI and the 6 EI and the 4 EI. So this is equals to this one. The second one is equals to the number 6. The third one is equals to the number 6, and the last one is equals to this number 4. All right. We enforce boundary condition at the base using the row and column elimination. So they are all gone. We keep only the movable point. And here it is determinant of this matrix. And we know that in order to satisfy this, multiply by U1, U2, and to get 0. You need to have the 0 determinant. You can do it into different approaches. The first approach, you have P over PE, plot versus the determinant of K. So let's start from P over PE equals to this value. Determinant is equals to this value. Just value. Okay. And then we increase 0.1. You can see that determinant change as you change the load. Now from 11, from about 12 reduced to 7. So we'll see 0.2. Oh, you get this one. 0.25. Okay, comes to 0. So it is too sensitive at that point. Make it 0.22. Point 0.23. It's not 0 yet. 0.24. Point 245. Let's try 247. Point 24999. So we expect the point where the value crosses 0. 0.2499999999. And 0.250001. Okay, and then we plot. Actually, you don't really have to plot now because you know that the value, the function value just cross 0 somewhere here about 0.25 exact. Okay, 0.25 of the PE, which is equal to pi square EI divided by 4L square. The 4, the K for the column with the fixed base is equals to 2, right? So the KL term as the denominator, when it square up, you get the 1/4 factor, which is 0.25. Okay, you can get it. This is by using the stability function. We will try the geometric stiffness matrix in parallel. So if we try geometric stiffness matrix, basically, by the way, if you use stability function, you can do it this way also. Plotting out like this is very good. It is foolproof. You cannot get wrong. The thing is that you need to work out on it. You just need to plot it. You can use the goal seeker. So if you go with the data, what if analysis, goal seek, and you need to set this cell to 0 by changing this one, and then go ahead. Yes, it is close to the initial value that I input previously, 0.1. So the goal seek just look up for something which is closest to the initial value, and then it turns out that the POPE has to be 0 to satisfy this 0 determinant. This is very close to 0, right? Let's point to and try it again. Can go seek with G10 found solution target value 0. Yeah, you can end up with something like this. Sometimes it is smart, sometimes it is not. 0.24. If you got to do it this much, then you don't need the goal seeker, right? It should be value 0 by changing this cell. This is 0.25 already, right? No. E to the minus 6. This is close to 0. It just run back to 0 every time. No, sorry. Okay, sorry. I'm confused myself. So this value is changed to 0.249999, which is about 0.25, and then this determinant is about 0. Okay, so it works. But sometimes if you have more than one root and it picks up the second one, so let's try. I think it could be going to somewhere like let's start with 1. Okay, and then we do the goal seek again. We need the 0 value by changing this cell. So let's see if it's gonna bring us back to 0.25. It brings back. Interesting. Let me see. 0.3. What do we get? Minus 0.5 to 10, right? 1 to 24, 2 to 15. Okay, better. 3. Okay. So let's start with 2.3. No. 2.1. Okay, let's start with 2.1. I think this is going to be the second root of the buckling load. So 0 and here. Okay, you get this second root 2.25. But you are not looking for the second root, right? Your structure is gone before. So if you use the goal seeker with the initial value which is not close to the root that you want, so it depends on how you put the initial over here. Goal seek will just look up and down and find the solution in the vicinity of the initial value you input, and you could be wrong. If you don't use it with caution, you could be wrong. But if you plot out the determinant, you can see how the function swing, and then you can pick up the right root. Okay, so just the tips, not the tips, but it is up to the, it is affected by the algorithm of the goal seeker. So if we use another thing instead of stability function, we try the geometric stiffness matrix. So the 12, I will have F12, F6, and F4, F2. So F12 is equals to 12 basically multiplied by EI over L square. Minus P. Multiplied by 1.2. Okay. If you look back, you find that one matrix is 12, another matrix minus P multiplied by 6 over 5. 6 over 5 is 1.2. So P multiplied by that 1.2. So start with P 0.1 like this. F6, so it is equals to 6 minus 0.1 multiplied by the P, which is the 1 over 10P. The 4 is minus 2 divided by 15 multiplied by P. I need to put 4 here, right? 4 minus 2, 15 multiplied by P. And last one, 2 plus P over 30. 2 plus P over 30. Right. What is that? Okay. Don't complain. Just this. And then we can set up the stiffness matrix using the stability function. Not stability function. This geometric stiffness. So 6, and last one 4. We'll be able to find out the P over EI over L square. Okay. So this P is actually P over EI over L square. Because if you recall, the left matrix is scaled by EI over L square. The right matrix is scaled by P. Then if I divide through by EI over L square, you have just the matrix that includes a parameter 12, 6 pure without any variable EI, without coefficient EI and L, right? And then the scaling of the right hand side matrix, the second matrix is P divided by EI over L square. So we will find out the value of P over EI divided by L square. Here, then we have determinant MD term of this one. So let's start with POP that care 0.1, you get 11, you get 0.2 next, tentatively it's gonna be more stiff, right? 0.25, let's see, still 10. Multiply by EI. Okay, okay, makes sense. 0.4. You got to keep in mind that the definition, this is not the P over PE, this is the P over EI over L square. So this is equal to 3.14 times, right? The EI over L square is not the buckling load. It is less than PE 3.14 times. So 0.6, let's see, 0.6 reduced to this value, 0.8, let me just try using this one first to see by changing this cell. About 248. Okay. This is one value. Then 1, pi square is 9 times, right? 1.3, I just waste time. 2.0, 2.2, 2.2. By the way, tomorrow I'll be in Chiang Rai, so we will not have class tomorrow. And you will not have structural dynamics tomorrow neither. Tomorrow will be like the free day. 2.5. Okay, so the value switch over here at the 2.48 or about 2.5. 2.4. Let me try 2.49. 2.49. 2.48. 5. What? 999. Not as small as that one. Okay. Right. So number swing over here this point. If you plot, you're gonna see the relationship. just like this. Is it wrong? No, because you are having different definition. This is P over I, this is P over PE. So in order to make this P over PE, you have to divide this value by pi square, right? You have just EI over L square. You need to introduce the pi square in there. And so you end up with the value around here, 0.25. A little bit above 0.25 as it is the numerical and as it is a little stiffer than the reality that we use the approximation of the geometric stiffness matrix, but usable, right? 0.25. You will not push yourself close to this value because buckling is the kind of brittle failure and there is no sign. Once you reach the bifurcation point, your structure just come down. You don't need to run. Then I think I can delete all this. So we can use this for the next example. Number 2. The problem that we want to play, second one is the pin column. Pin at the top, pin at the bottom. You have only 2 degrees of freedom. But the 2 degrees of freedom are U2 and U4. Just rotation, displacement are all restrained. So that come from F4, come from F2 and F4. I reset the value to 0.1 again. So basically 0.01. Let me just use the goal seeker, put the number 0 here, and the line here, the second element, we are not using it now. We might use it later. So don't get, well, you might wonder why do I keep it? I'm not using it, all right? Right now, because we have 1 element, but if we discretize into 2, we're gonna use it. Okay, go seek, and there you go. We find that P over PE ratio is 0.99999, which is 1. And that makes perfect sense because this pin condition, you will get the buckling load equals to the Euler buckling load of the pin condition. Alright, you cannot run away from this. You cannot get other number. If we use this, if we look into the geometric stiffness matrix here, I change to F4, F2, F2, and F4. Let me start with 0.001 and then what if and go seek, and we need 0 and changing this cell. Boop. Okay. So PE ratio is this value. If we take this value divide by pi multiplied by pi, so by pi square, you get 1.21. nothing is wrong here. You really get 1.21, which is more stiff, well, not the stiff, which is higher capacity than we expect, right, for the pin column. So how do we alleviate this situation? It is all because of the discretization. Previously, in the former case, when you fix the base of the column, and the point where you set up the degree of freedom is actually the point where you expect the largest deformation. Cantilever column moves the most at the top, and you have the degree of freedom set up at the top. So that picks up, that is very sensitive to the buckling. Whereas this case, we have pin and pin. You pick up the rotation, but that two rotations at the top and bottom is not as accurate, not as sensitive as the middle column displacement. So it gives you higher buckling load, 20% more. Then to solve this, we use two structural elements in this regard. So we insert the shape. Okay. We will have two members. The middle point we discretize. You have the top and you have the bottom. Keep in mind that right now the L we have in here is 0.5 L. So first member, you don't have the first DOF, you have rotation, and you have the third DOF, you have the rotation. And then the second member, you have this displacement, degree of freedom, and rotation and rotation. So you have 1, 2, 3, 4. This is going to be the 4x4 matrix. Start with dropping in 0. So this is equal to the what? Second, which is 4, right? 4 EI over L minus 6, and then 2, right? This is equals to this, this is equals to this, this is equals to 12, and that is equals to minus 6, equals to minus 6, 2 EI, yeah, minus 6, and then equals to the 4 EI. So this part account for rotation here, displacement here, and rotation here. The next part, you have the displacement here, which is the contribution from the member at the bottom. So this one you add up with the 12 EI of the second element. This part you add up with the 6 EI of the second element. Okay, this is equal to this already. this part here is add up with what is this one? Rotation, right? With the F4. Okay. This part here is equal to what is this? The 12, 6, and 6. This is equals to this one. This is the rotation, right? This is the 4, this is the 2, right? And it has this one, the 2. Okay, this one is equal to this one, and the last one, this was supposed to be F4. Okay, so we will go seek for the determinant of this matrix MD term. Uh, 0.1. And we go seek. Go seek. We need that cell to be 0 by changing this cell. Okay. This is the P over PE ratio. Okay. Why do we get 0.25? Because right now our PE is defined by pi square EI over 0.5 L, the whole thing square. So 0.5 square point, you get 0.25. So basically your buckling load is equal to 4 pi square EI over L square. Then you get that buckling load multiplied by 0.25. You need to get the 4 multiplied by this 0.25, and then you get 1 point something. So you are about just 0.7% off, which is very reasonable, acceptable for the engineering design. So basically, if you use the structural analysis program, you want to account for the P delta effect by geometric stiffness matrix. You cannot just discretize your structure using the node that you have from the discretization you might be okay with in the case where you don't consider the second order effect. Let's see what I mean by that. If you have the node in your structure like this, sorry. Okay, node might be a little bit just big. So if you discretize and put the node in a conventional way, you just put the node at the junction between the beam and the column, so it just look like this. But if you want to account for the second order effect, and you have seen here that you get a very bad overestimation of your structural capacity you try to incorporate the second order effect, but the node, the degree of freedom that you have to account for second order is not at the sensitive location. So it does not pick up the effect well. The consequence is that your structure is stronger than the capacity you're supposed to have. That's the main thing. So to pick up the second order effect better, put this in. Discretize and put the node at the middle of your column if you want to run second order analysis. Generally, many of you gonna use the program when you work on your thesis research. You run nonlinear time history, you try to capture the nonlinearity, and you say that you turn on the second order effect in the analysis program. But if you don't discretize your column this way, it doesn't pick up the second order effect. And then you might get the benefit from turning on the nonlinear stiffness, geometric stiffness in the program. The benefit might be just a little bit. You don't get the full benefit because you don't allow this degree of freedom to be in your calculation, right? If you can see here, you look at the frame structure, axial load in the beam might not be so high in general, but the axial load in the column is large, and without the discretization over here to pick up the large deformation which is going to be at the middle of the column, then your system is not sensitive to the P delta effect, and that's the waste. Okay, you can get wrong by as many as, well, you have seen 20% already. It could be more than that, right? So be careful. It is not like you just get the program and go click the nonlinear geometry and it's gonna do everything for you. You need to have some understanding that it is sensitive to the mesh also. Okay, this is example number 2. So let's proceed to number 3. Number 3 is the fixed case. Second one is a pin. Cantilever. Fix and fix. For fix and fix, we need to discretize at the middle. So I take the picture from here. You don't have degree of freedom at the top, you have only just degree of freedom at the middle. Bottom is also locked for a fix. Then 2 degree of freedom. First of all, it is the lower corner of the first element, right? So F12 and then minus F6 and then minus F6 and the other one F4. Oh, I think F4, this one is wrong, minus F6. Okay, this is a contribution from the first element. The second element, you have the two upper corners, so you add up with the F12 of the second element Over here you add up with the F6, so it cancel out to 0. You add up with the F6, it cancel out to 0, and then the last one is the F4. Okay. So let's do the goal seeking for the buckling load. Go data, what if analysis, goal seek, you need the 0, and we change this one. Okay. The PO/PE ratio is 1. Now, keep in mind that you discretize the member into two pieces, L/2 and L/2. So the buckling load over here in this definition is equals to 4 times pi square EI over L square, as your effective length reduced to 0.5 L. Right? Buckling load increased to 4 times. So your PO/PE at the buckling of this system is equals to 1, and then multiply by 4 pi square over EI over L square, which fit with what we used to derive. Right? Then I think I just delete this because we are not using this one. Just confuse you when you it doesn't go. Okay, fine. Don't do the cleaning up here. Let's use the geometric stiffness matrix. So we have 12. We have the -6. We have the -6, and we have the 4, and we have this part add up with the F12, and then this gonna clear out. This is like the one before, so plus the F6, and this is added up with this one. Okay. And what if go seek this value? We need this. Oh, okay. We need PO/PE ratio turns out to be 1.01, about 1% off, 1.3% off. Not bad, still acceptable, very close. And again, PE in this definition is equals to 4 pi square EI over L square. Match. Then we can try the frame. Okay, good. So we try the frame here. In the frame, the first 2 degree freedom of the column is at the top, and then the horizontal, maybe I draw it here. we have the horizontal element and we have the vertical element. Both of them we have the fixed support down here and the roller over there. So this one contributes in degree of freedom in X and rotation. This one contribute in rotation here and rotation there. So in total we have 1, 2 and 3 degree of freedom. 3 degree of freedom system, we set up the stiffness matrix. So let's start with the first one here. We can assume that this horizontal member is axially stiff. Okay, so axially rigid, you don't have deformation, relative deformation between this point and this point, no stretching. This is equals to 12 EI. This is equals to 6, right? Equals to this one, and the last one is 4. Okay, and then contribution from this member, just rotation here and rotation there. So this add up with, well, okay, this add up with F4. We need to use the second element. Right now you don't have the same axial force. We will apply the load on the column downward like this. So the second element, you don't have axial force. So we need to take the entries from the second one. And let me emphasize you here that the Eigen buckling problem, it depends on how you apply load. For this case, you have just one column. It's not possible to apply axial load to the other element. But sometimes you have more than one column system, and you might apply the load in the column differently. You have different magnitude, but it sticks to one pattern. For example, if you have 2 columns of the identical properties, EI the same and length the same, right? 2 columns are connected with one beam. You can put 1P on one column and 2P on another column. You will get one buckling load. And if you change the distribution of the load, like 1P and 1P to both columns, you will get the different value of P. It depends on the distribution you have. It does not just give you like, you have 2 columns and then you have just one set of buckling load. It's not going like that, because you have the freedom to apply the load on 2 columns differently. So if you have the load ratio prescribed at the beginning, how much on this column and how much on another column, then you get that Eigen buckling load for that case only, and you can change the distribution and you will get the different number. We can try. I think you might not see the picture for now. We will try this on the next problem. Okay, and then we set this MD term. And we're gonna do the goal seeking of by changing this POPE for element number 1. Another element you don't have axial load. Okay. So the buckling load is about 0.61 times the PE. Is that make sense to you? With the cantilever column, you get 0.25 as the effective length is equals to 2L. If you pin at the top, you have pin case, you get 1.0. This case here is better than cantilever column, right? The load is greater than cantilever column because you apply the rotation restraint at the top. It is like the cantilever column with the rotational spring attached at the top. But the displacement, horizontal displacement, is not restrained, so it is not as good as the case where you have the fixed cantilever support with the pin roller at the top. Okay, so well, makes sense. 0.6 somewhere. Let's take a look at the counterpart here. So this system we use the geometric stiffness matrix to cast to set up the stiffness of the structure. So we have the top one for the column, the bottom one for the beam. This is for a beam, okay. 12 and then 6, and this is for the 4. For the 4, you add up with the 4 from the beam. Here is the 2 from the beam, 2 from the beam, and 4 from the beam, equals to m, the term of this one. And then you use the goal seeker. .61, not bad, huh? 0.616 and 0.6109. Why isn't it bad in this case? Again, you have just the rotational, it is equivalent to rotational spring attached at the top. In this case, when the system buckle, the displacement, the highest displacement occur at the top over here. Thus, you are setting up the degree of freedom right at the sensitive point already. And then your buckling load is well predicted because of the way the setup, which is just a fluke, well, just lucky. If this point is not this one, if it is this one, the prediction will not be as good as the stability function because the maximum deformation will be in between. When this system buckle, the max is over here. It is not like just go like this. Then you will need to put another point in the middle. So let's try. We'll put it back in the original way, so when you have this file you will not be confused. This case, we expect that the solution will not be that good. Okay, so make it something like this. If we have this one, you have rotation and rotation. You don't have this column, right? We restrain the horizontal deformation. We don't allow displacement in the x-axis, so I took off the degree of freedom, rows and columns for this degree of freedom. We have just two remaining, and then we get the new determinant figure out over here. I put the 0.1 there. Let's guesstimate first. This one is like the case where you have fixed and pin roller, okay, at the top. That case, the effective length is about 0.7, right? 0.7, when you square it up, you get about 0.49, which is 0.5. 0.5 is the denominator, so your buckling load of this case is going to be 2 pi square, approximately. It is 2.05 pi square EI over L square. If you don't attach to the beam like this. If you attach to the beam, that means you have that case with the additional rotational spring stiffness put at the top. So buckling load was supposed to be more than 2.05 pi square EI over L square. So let's see. What if go seek and we need 0 by changing this cell? Yeah, 2.73. If the stiffness is really low, then you right now we take the EI out of the consideration. Not out of the consideration. We try to pull everything out, but later I think I'm gonna set up the system such that we don't really have to have the common EI. If I want to change the stiffness, the EI of this beam to somewhere which is very low, okay? Very low EI, then you have low rotational spring stiffness, and as you decrease it down smaller and smaller, you'll be getting the buckling load closer and closer to 2.05. Anyway, let's do it in the next one. So this one, clear this, I change this. So we don't expect that the geometric stiffness matrix with the setup like this, having just 2 degrees of freedom, will work as good as this stability function on the left hand side. So what if go seek, we need the 0. You should end up with the number which is well, let me start with small first. Okay, so big, you will get something more than 2.6 over there. Wow. Okay, you get this one, pure PE over here, 5.3. Not good at all. Sometime maybe the guess, if it is not good, let us try something close to, this is 5.3. If we try something close to 2.7, that makes the 26. Okay, let's see if I put the initial guess which is close to the buckling load of the other one. I'm not sure if it jumps to the second root already or not. This is quite high. Okay, still there. 5.3. If you want to investigate further, just start from 0, 1, 2, 3, 4, 5 and then plot it out and see if we can try just quick. You don't need to plot it out. 0.1 you get 27. 0.5 you get 27. 1 you get 27. 1.5 okay. 2 26. 3 26. 5 25. 7 24. 9 23. 11 22. 13 still big. 17 8 you get 18. 20 you get 17. 25 14. 30 get 12. 35 you get 9. 40 you get 6. 45 you get 4. 50 you get 1. Okay, so that makes sense. 52 gives you the first root. Now this is ugly because one case you get 2.7, another case you get 5. This is wrong drastically. So let's try to fix it. Where can I delete? Okay, delete, shift cell left. So we need to make a 2 discretization of the column must be made into 2 members like this. Okay. So we can pick up the displacement at the middle of the column, and that is the sensitive location. If you want, you can go a little bit like 0.4L and 0.6L. Okay, it doesn't really have to be right at the middle because the maximum deflection might not be exactly at the middle, but if you put the degree of freedom in that vicinity, you can at least pick up the effect. Not absolute max displacement point, still fine, but you are close to that point, you will get the influence, the contribution from the large deformation and large P delta at that area. Okay, so we will have 2 columns stiffness matrix and 1 beam stiffness matrix. So for the column, I will set the P equals to something times EI over L square. And then we will get the stiffness matrix of column. And K for the beam. Everything will be scaled by EI over L square out there. Should it be? No. If P is in this scale, then everything will be cancelled out, right? Okay. The EI and L will cancel out, and you will keep just the number. L column is equal to something that is scaled by L beam. is also scaled by L. So L column is equals to 0.5 and L beam is 1.0. P beam small 0.001. And P column 0.001 as well. Okay. Let me just give the EI column and EI beam. EI for a column so right now 1.0 for both. Oh, why is it? Okay. So as you take out as you will take out the term EI and L. Okay, so let's take a look at this one here. The first on the left is the linear stiffness, and the second one is a geometric stiffness. So first one, this is equal to 12 times the scale of EI has to be in here, right? Divide by the scale of L has to be in here, Q. Previously we deal with just one element. Now you have two different elements. You might have different EI, you might have different length. So I need to just push all the scaling of the EI and scaling of the L inside the matrix, and then we just pull out the coefficient E, I, L outside and be able to calculate, put equations together. Next one is the 6 times EI column over L square. This is equals to minus 12. This is equals to the 6 equals to the 6 equals to minus 12 equals to 6 equals to this one equals to 4 is not there yet, right? Minus and then minus. Okay, next will be 4 times EI over L. This is 2 times EI over this L, and then equals to this equals to this. Okay. Likewise for the beam, beam 12 times EI beam over LQ, L beam Q, 6 times EI beam over L square, and then 4 times EI beam over length of the beam, and this is 2 times EI beam over length. Okay, and then we just copy equals to 6 equals to minus 12 equals to 6 equals to 6 equals to minus 6 equals to minus 6 equals to minus 6 equals to minus 6 equals to 12 equals to 2 equals to 4. Okay, first part done, and second part, this one here is the where is it? We need to incorporate the length scale, so 1.2 divided by the length. This is 0.1. This is minus 1.2 divided by the length. And okay, this is 0.1, right? 0.1. Okay, so this is 0.1, this is this one, and this is equal to 0.1. This one is equal to 2 over 15, and then multiply by the length, right? Yeah, oh, okay. 2 over 15 multiplied by the length. This is equals to minus L over 10. L cancel out later. This one is what? Equals to minus the length divided by 30. Okay, so the length divided by 30 is coming down here. This is this. What else? Minus L over 10 and then 6 over 5, which is this one, and this is minus L over 10 and minus L over 10. Okay, right. So if you have just one, everything just come back to normalcy. 1.2, 0.1 minus 1.2, 0.1, 0.1, 133, 2 over 15. Okay. Right. And then this one equals to 1.2 times 1.2 divided by this equals to 0.1. Okay, equals to 0.1 equals to 0.1 equals to minus that one. This is this one. Okay, minus, oops, 1.2, this is equals to 2 over 15, 2 divided by 15 multiplied by the length, and this is identical but negative sign of this one. Right. This one has to be negative of that one. L over 10 minus this minus L over 10, okay, equals to minus L over 30, right, minus L over 30, and equals to minus 0.1 and equals to minus 0.1. Okay. Whew. All right. So this is basically, if we keep it this way, basically scale by EI over L square, and this is also scaled by the same thing because your P is the same. Insert shift right. Okay. Your P is given by this value, which is scaled by this EI over L square, right? So we substitute the P into this side here. So we multiply the whole thing to this matrix. It is P over L. I push the L inside, and then the L, we have the parameter that scale the L coming inside the matrix on the right hand side already. So finally, you can come up with the final stiffness matrix that incorporate the linear term and the geometric nonlinearity terms. Oh, you got to minus because your P is the positive value. Compression is a positive value. Okay, so that's for the column, and we have the stiffness matrix for the beam. The beam is equals to this, add up with, oh, not add up, minus this part as well. Okay. We got to take this one here and multiply. Okay, and you got to lock this cell. Okay, I've got to fix that on this one. We need to scale by P column, right? Oh, I didn't lock the cell. Okay. Then, if you put the very small EI for the beam, you can reduce the effect from the rotational restraining of the beam. We will play with that, could be later, but first of all, let's set up the stiffness matrix for the new system that will incorporate the transverse deformation of the column at the middle. If you set it up 0.4 L for the upper part and 0.6 L, then your stiffness matrix, you're gonna make 3, right? Column, you will have two matrices. So you just copy this, and then your EI might be the same, but L could be different, and then you assemble things in. But I am just kind of lazy, so I break it in the middle, and then I just have one stiffness matrix that would work for both members, but you can do the other way. The further from the point where you have the maximum moment, then the less accurate the solution you will get. So for example, if you have maybe the upper column length equals to 0.8 and then the node is coming down here, then this is quite a silly option to do, right? Because you don't think that it will deform much at this point. So somewhere close to the max, actually too close to the max, top might be 0.4 and here might be 0.6, because the restraining effect here is not as much as the restraining by the support. Well, anyway, 0.5 will work. It is not that sensitive to this choice of location if it is around the middle. So the system, we have how many degree of freedom? 1, 2, 3, 4. 4 degree of freedom in total. So let's drop in one by one. This member, the first one, well, I think I have to define the degree of freedom for you. And then I delete this because you might get confused. Well, okay, just scale. Okay, so U1 and U2, no. Where was it supposed to be? U1, U2. Oh, you have just one U1 here, U2, U3. U2 is a translation, and here is the U4. Okay. U2 transverse deformation, U3 rotation. Okay. So we take U1 rotation and displacement. Okay. So this is equal to this point here, right? This is a contribution from the top column. You don't have displacement U1, the first displacement of this top column, but you have the second displacement at the ending node and rotation. So we take the this part here and put them down there. Second one, for the element number 2, you have the contribution for the first and second degree of freedom, and that is going to be in here. So this one you will add up with okay, this point here. So copy and copy. Okay, you get the contribution from the second one now. How about this U4? U4 and U1 are related, so U1 will be added up with this number, and this one is equals to this number. This one is equals to this number. This is a rotation of the beam, and the last one is okay. And then MD term of so we need to data. What if cosec could have a 0? oh, and then changing the cell for column. 28, if you divide by pi 3 pi 2.84 2.73. Now much better, now makes sense. If you end up with 5 something, which is the double of the value that should be, that is not good. Well, but you can see here that when we use the stability function generally it gives you the exact solution due to the way we derive it. We don't involve any approximation of the deformed shape in the formulation like geometric stiffness matrix. So geometric stiffness matrix gives you some value which is generally higher than the value we expect from the closed form solution or by exact calculation like the stability function. You don't need more as many degree of freedom when you use the stability function in comparison with the geometric stiffness matrix. The thing is that as it is computerized, the structural analysis is not done by hand in general. Your software will take care of it. So you will deal with the geometric stiffness matrix more than the stability function. Stability function is not easy to deal with as it has the trigonometry function in there, right? And sometimes the function fluctuates, so it jumps at some value. Stability geometric is better in that regard, so it is quite stable, it is not fluctuating much. But to use it and to make sure that you squeeze out the performance, the capacity of the geometric stiffness matrix as much as possible, you need to be very careful with the mesh, the choice of your mesh. And the rule of thumb is to just include the node at the middle of the column. You never know, some case it might be sensitive to the node at the middle. In some cases it might not be. If you have the column, 2 columns, and then you have the beam at the top, and if the buckling mode involves something like the sway mode, okay, you might not have the point at the middle. It might pick up the buckling load that is quite accurate. But if the system is not failed by the sway mode, it is by the buckling at the middle of the column, then if you don't incorporate, don't make the node at the middle, you don't pick up, and the phenomena that involved with the buckling is not picked up, you overestimate the buckling load. So that's the way it works. All right, so we are just good. I think we are having 10 minutes to get out of this room, which is great, and we wrap up everything we were supposed to do for today. So next class will be on Thursday. We don't have tomorrow class, just to emphasize again. Next class on Thursday in this room, we will look more into the frame structural analysis using the stability function or geometric stiffness matrix. Also, we will look more into the buckling load of the frame. This is just the simple kind of frame we will deal with, just 2 members. Then we have more and more members, and then we apply the load. We have some sort of configuration of load, and then you will see that changing the configuration will also change the buckling load. And in the case where you have the iterative solution, I think that might be covered in the next class. So for example, if you don't apply the load right at the top of the column, so you might have distributed load, or maybe the load applied on the span. So first of all, you don't know how much load comes to each column, right? Because you have not done structural analysis. But you have to do structural analysis. But you don't have the P information. So we will start from the guess value of P. Once we finish the first round of analysis, you'll be able to determine the axial load distribution in all columns. But that estimation was not precise because you initially assumed the value of P. Okay, so the stiffness was not correct at the first analysis, but then you get some value. You will update your analysis using the calculated P distribution in each column for the second round. And then you will get the new set of P, which is not so far different from the first set of P now. And then you refine your solution. So we call it the iterative solution. You will not get one solution in just one step. But as you refine your calculation, you get better and better and better. So you get the converge. Solution will converge to one value, right? And you'll be able to determine, the buckling load in a different way. Because right now we do the Eigen buckling. Later we will not do Eigen buckling anymore because it's not just the one sharp bifurcation point. The system may deform and then undergo very, very large deformation. So we will figure out where we will allow our structure to withstand the load, because when deformation is too big, you lose the stability and so on and so forth, right? But you don't have the bifurcation point and it's no longer Eigen buckling. Well, why? Because if you look at the setup Ku equals to F, your F will be no longer 0, okay? Because you have the span loading. If you put the distributed force on your beam, then you have span loading. So your span loading will not make your force vector be 0. You will have something in that force vector. So you will solve and you will get the displacement solution U. But when you will solve for the incremental force vector, so you start with small value and then you keep increasing the force, and then you have the deformation that is increasing with the force up to one point where the stability is triggered. You are close to the axial force that caused the problem. Then deformation will be no longer linear with the load. Deformation will be exponentially growth with the load, and that is the bad situation. Okay. This is in the air. It's just the premiere, okay, of the next class. So you will see the real situation when I draw everything up. All right. Okay. See you on Thursday.